Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving into a fascinating article. Why does integer addition approximate float multiplication? It's all about a surprisingly effective hack for approximating float multiplication using integer addition. Pretty cool, huh? Intriguing, right?
Absolutely, I'm eager to hear this. So the core idea is replacing the computationally expensive float multiplication with a simpler integer addition. How accurate is this approximation, though?
That's the million-dollar question. The article presents a function that casts floats to integers, adds them, adjusts the exponent, and then casts back to a float. The initial approximation, just adding exponents, gets you within a factor of 2. But, surprisingly, a refined version gets within 7.5% accuracy.
Whoa! 7.5% is remarkably close. What's the secret sauce? Some clever bit manipulation, I presume?
Exactly. The magic lies in understanding how floats are represented. The exponent is added directly, mirroring the logarithmic nature of multiplication. There's also a clever mantissa offset, a constant value that helps fine-tune the approximation. The article even shows a graph illustrating the relationship between log, 1 plus x, and x, which explains why this simple addition works so well.
I see. So it leverages the fact that log, 1 plus x, is approximately equal to x for a certain range. But are there any significant drawbacks to this method? The article mentions some limitations, right?
Oh yeah, there are some caveats. The biggest issue is handling exponent overflow and underflow. Underflow, especially, is a problem because it can lead to wildly inaccurate results. The article presents a more robust version that addresses underflow, but it's more complex. Also, it won't be faster than native float multiplication in most cases. And it prevents the use of tensor cores.
So while elegant in its simplicity, it's not a general-purpose replacement for float multiplication. It's more of a niche optimization, perhaps for power-constrained environments where the accuracy trade-off is acceptable. What about the mantissa adjustment? How was that constant determined?
That's a great point. The mantissa adjustment is empirically determined. The author tried various analytical approaches, but they didn't yield satisfactory results. Ultimately, they settled on a constant that minimized error across a large set of randomly generated test floats. It's a bit of a brute force approach, but it works.
It's interesting how such a seemingly simple idea can lead to such a surprisingly effective, albeit imperfect, approximation. It highlights the intricate relationship between integer and floating point arithmetic. So in summary, while not a universal solution, this integer addition method offers a potentially useful trade-off between speed, power consumption, and accuracy in specific scenarios.
Precisely. It's a clever hack that showcases the power of understanding the underlying representation of floating point numbers. While not a silver bullet, it's a fascinating example of how seemingly disparate mathematical operations can be surprisingly interconnected. Thanks for joining us on Tech Bytes and News. We hope you enjoyed this deep dive into the world of floating point approximations. Goodbye.
Bye-bye.